Great.
All right. Hello, everybody.
Hi, everyone.
Okay, I can see we have 29 people. Oh, okay, more, 31 people watching us. But we are going to wait just a few minutes more because a lot probably still joining.
Yeah, sounds good.
Okay. How are you, Jorge, today?
Yeah, pretty good. It's a really sunny day here today in Bolivia. So we have a pretty good weather.
Great. Okay, I can see people coming. Hello, hello, how are you? Okay, I think it's time to start. So hello everyone, welcome to Functional World, the third edition. Today we're going to talk about functional programming in ZIO with Jorge. Our presentation will take about 1 hour and 10 minutes, and I'm sure it's going to be great. I'm going to give you a few useful links in a chat, or also you'll find it in a description of the video. So links like ZIO Discord or our workshop offers and that kind of stuff. About the logistics, please ask all of your questions in the chat, or also you can ask on the Twitter, and I'm going to grab and speak all of those questions, and Jorge will answer them later after the presentation. Yeah, I think it's time to start. Jorge, mi amigo, are you ready?
I'm ready. So thank you, Amiga Maya. And thanks, everyone, for joining this presentation today in Functional World. And well, we'll be discussing about functional programming 101 with Scala and ZIO. So I hope you enjoyed this presentation. And as Maya has mentioned, I'm going to be answering any questions you have at the end of the presentation. So my name is Jorge Vasquez, and I'm a Scala developer at Scala. And what's the agenda for the presentation today? Well, first, we're going to discuss about some basic concepts around functional programming. Next, we're going to see some basic concepts around ZIO, the library. And finally, we're going to do some live coding. We're going to implement a Tic-Tac-Toe game. So wish me luck on that, and I hope you enjoy seeing how we can use ZIO for implementing real-life applications. So what is functional programming? Let's start by that. And functional programming is a programming paradigm where programs are a composition of pure functions. So the most important concept to grasp here is what is a pure function. So the characteristics of a pure function are the following. A pure function must be total. It must be deterministic and depend on its inputs only. And it must not have side effects. So those are the three characteristics of a pure function, and now we are going to discuss them one by one. So a pure function must be total. What this means? This means that for each input that is provided to the function, to a pure function, there must be a defined output. So a very simple example, we have this divide function. It just divides two integers. But what happens if we try to divide 5 by 0? We're going to get an arithmetic exception because we're trying to divide by 0. So this means this function is not total. Hence, it's not pure because it's not defined for the cases where b equals 0. So the signature of this function, which is impure, is telling a lie. Why? Because if you just look at the function signature, at the definition, in theory, for every pair of integers a and b you receive, you should get another integer, right? But that's not entirely true, because we have seen that for the case that b equals 0, we are not going to get an integer. We're going to get an exception. So because of that, every time we call this function, we will have to be very careful. So we have to take into consideration this case, and we must handle it appropriately. And if we forget to do that, runtime exceptions are going to happen. So the compiler will not be able to do anything to help us to avoid this. So exceptions will happen at runtime, and that's something we don't want to happen. So we have here another version of the divide function. And in this case, it doesn't return an integer, but it returns an option of an integer. So we have, in some cases, for example, when b equals 0, we're going to get a known value. And in the other case, where b is different than 0, we're going to get this, the division of the integers encapsulated inside a sum. So now if we divide 5 by 0, we're going to get a known value. We don't get an exception anymore, but we get a concrete value. So now this function is total. The function's signature clearly communicates that some inputs are not handled. So now just by looking at the function, at the signature, without looking at the implementation, we can know that there are some cases that we're not going to get an int. That's why the function says that it returns an option of an int. The compiler then will force us to consider the case in which the result is not defined, because now we're returning an option, we're not returning just an integer. And because of this, there are no runtime exceptions. So that's really great. What's other characteristic of pure functions is that pure functions must be deterministic and depend only on its inputs. So for each input that is provided to the function, the same output must be returned, no matter how many times the function is called. So for example, here I have this generate random int function that, well, you can see several things here. One is that the function doesn't receive any input parameters. And internally, it's using this instance of Scala util random and calling next integer on it. So when I call this function the first time, I'm going to get a value. The next time, I'm going to get another value. And the same will happen every time we call this function. So it's not deterministic. So here, the signature is misleading again. Why? Because, well, there is a hidden dependency on this random object. So in theory, generate random int doesn't depend on anything for generating random integers, right? Because we don't need to provide any input to the function for calling it. But there is a dependency, and that dependency is hidden inside the implementation of generate random integer. So the signature is confusing, again, misleading. And it's difficult to test because we can never really be sure how the function will behave, because every time we call it, we get a different answer. So here I have another version of this generate random int. For that, I have this custom random number generator, RNG. By the way, this example of this random number generator comes from the Scala Red Book. So I'm just using it here. And you can see this new implementation of generate random int receives a random number generator as an input. So now the not hidden as it was before, and returns two values as a tuple. First, the random integer we are generating, and next, a new random number generator. So now what will happen? Here, I'm instantiating a random number generator, and then I'm calling generate random int with it. So you can see I'm having number 1 that was generated, and a new random number generator. If I call the generate random int function again with the same random object, so it's the same input as before, I'm going to get the same output as before. So this is different now we get deterministic results. If I want to have a different result, I need to provide a different input. In this case, another random generator, this random2 value, and just in that case, I'm going to get a different value. So now this new version of the function is deterministic. And finally, a function must not have any side effects. So there must not be any memory mutations. So that means you can't overwrite any value in memory. You can, for example, increment it. That's not allowed in pure functions. You can have interactions with the outside world, such as printing messages to the console, calling external APIs, or querying databases. Pure functions are not allowed to do that. A pure function can only work with immutable values, so values that don't change, and return an output for a corresponding input. And that's the only thing they are allowed to do. For example, this increment function is not pure. Why? Because it's mutating the value of this a variable. So here you can see it's getting incremented according to the value passed as this inc parameter. So this is not pure because it's mutating a region in memory. And also, we have this another function, this add function, that calls this print line message, right? And this print line is interacting with the outside world, printing a message to the console. So because of that, this function is not pure. So well, now we have seen the characteristics of these pure functions. So now let's see what are some differences between functional programming and object-oriented programming. First, functional programming works always with immutable values. And in object-oriented programming, we generally work with mutable variables. So that's a very important difference. Then in functional programming, side effects are not allowed. In object-oriented programming, we almost always have side effects. How we do iterations? In functional programming, we use recursion. And in object-oriented programming, we use loops. For example, while loops, for loops, do-while loops. How is state managed in functional programming, the state of our applications? Well, the state is just a pure value that flows through pure functions. So it can work as input or output to pure functions. And in object-oriented programming, we generally have a state that's shared by several objects. So for example, we have singleton objects that are accessed by several parts of our application, mutating some regions in memory. So that's different. What are the key elements in functional programming? They are immutable values and functions. In object-oriented programming, the key elements are objects and methods. And we can say something else here, and is that functions in functional programming are also considered values. So in functional programming, functions are first-class citizens. And what does that mean? It means that a function, you can store it in a variable, you can pass it as input to another function, or you can have functions that return another functions as values. So actually, the key element in functional programming is just values, immutable values, where functions are values as well. So I think I remember John D. Gause mentioned this value-oriented programming term in one of his talks about ZIO. So another interesting name for functional programming could be that, value-oriented programming. And well, functional programming is really suitable for doing parallel programming. And object-oriented programming is not so much, because in object-oriented programming, we work a lot with mutating variables. So that means we can have awful race conditions in concurrent scenarios and problems like that. But in FP, we can avoid all of those problems. So what are the benefits of functional programming? First, local reasoning. And what does that mean? It means that because you have every pure function just depends on its inputs and outputs. If you want to understand what a function does, you just need to look to the inputs, to the outputs, and its internal implementation. You don't need to look anywhere else. Like in object-oriented programming, sometimes the behavior of a method depends on some variable that's inherited in some part of a really long inheritance hierarchy, for example. So you sometimes need to check other parts of the code to understand what a method really does. But in functional programming, you shouldn't need that. You just need to do local reasoning. Then there's this other interesting concept of referential transparency. I'm not going to give the formal definition here, but I can say that referential transparency means fearless refactoring. What does that mean? So if you try to refactor your code, for example, you are deleting a method, a function, and you want to replace all the usages of that by its internal implementation. The meaning, the behavior of your application won't change because we are just working with pure functions. In object-oriented programming, it's typical that sometimes you try to do some refactoring to your code, and because the code is full of side effects, sometimes your application starts doing things that you didn't want to. So in object-oriented programming, you have to be more careful when you're doing refactoring. In functional programming, you can refactor without any fear. Conciseness, this means fewer bugs, because we can write programs that are more concise. That means we have less places where we can mess up, so fewer bugs. It's easier to test. Applications behave more predictably because we have said that pure functions are deterministic, so the whole application will be more predictable, and allows us to write correct parallel programs. As I've mentioned, having this limitation of not being able to use mutable values gives us some great benefits when trying to write parallel and concurrent applications. Okay, so all of that sounds great, but how can we live without side effects? Because we need to interact with the outside world. We need to get input from the users, from a web page or from a console, or we need to call external services. We need to call databases. So, but we're saying that pure functions can't do side effects. So how can we work with this? So the trick that we use when writing functional programming applications is that we can write functions that we don't write functions that interact with the outside world, but we can write functions that describe interactions with the outside world instead. So that's a subtle difference. Instead of having functions that do side effects, having functions that return recipes of how to do side effects. That's a very important difference. And these descriptions of interactions with the outside world are called functional effects. So these functional effects are immutable values that can serve as inputs and outputs of pure functions. They are executed only at the end of the world. And what is that term end of the world mean? It means that you can write your whole application using just a functional programming style. That means just use pure functions. None of them executes any side effects. They just return descriptions of doing side effects. But there is a moment in the application, a very point, where those descriptions get translated into actual side effects. So they get executed, and you start calling external services, external databases, and things like that. And that's why it's called the end of the world, because it will be the end of the functional world, right? It's the end of the pure world where you start to execute those impure side effects. So putting this in practice seems a little difficult, right? So in theory, okay, the idea is simple. We can write these descriptions, but how can we actually put that in practice? And this is where libraries like ZIO enter into place. So ZIO is a library that allows us to build modern applications using the principles of functional programming. It allows us to do applications, to write applications that are asynchronous and concurrent using a fiber-based model. I'm not going to show this in the live coding today, but it's good to mention that this is the main characteristic of ZIO. You can write really, really concurrent applications in a very elegant way and using fibers instead of threads. So you can think of fibers as lightweight threads. So you can have applications with millions of threads and running them without any problem. The same wouldn't happen if you try to work with threads because they are really, really heavy. So this is a great characteristic of ZIO that if you are just starting with the library, it's a good, very good characteristic to explore. Next, it allows us to build resilient applications. And that's because ZIO leverages the power of Scala's type system. So we're going to see more of this when we implement the application in the live coding session. We are going to see how ZIO can help us to make more resilient applications, how we can handle errors in a very elegant way. It also allows us to build efficient applications. So a very important thing in applications is that they never should leak resources, right? So for example, if you open a connection to a database, or you open a connection to external server, you open a file, you want to handle those resources appropriately, right? So you want to close the database connections when they are not being used. You want to close the socket connections when connections to external servers are not being used. If you open a file, you want the file descriptor to be correctly closed. So normally we have to do all those tasks manually. And if we forget, we start having applications that leak resources. And that in time that can produce some performance issues. ZIO allows us in a very elegant way, very principled way, to build apps that never leak resources. And the library itself helps us to do that. And well, also ZIO helps us to build applications that are easy to understand and test, thanks to superior composability. What does this mean? It means that you can build your applications using these functional effects that are descriptions of interactions with the outside world. You can have several tiny descriptions and combine them just like Lego pieces and have your program as a big description of interactions with the outside world. So that's really easy to understand. You just need to know how to combine those descriptions. What are the options that ZIO gives you to combine those descriptions, those Lego pieces? So that's really, really powerful. Okay, so ZIO, the library, contains a core data type that's also named ZIO. So ZIO, the data type, is a type that has 3 type parameters, and it represents a functional effect. So ZIO is a functional effect. You can think of it as, well, with this mental model, you can think of the ZIO data type as a function from a type R that returns an either of an E or an A. That means a ZIO effect requires an environment of type R to execute. It can fail with an error of type E, and it can succeed, return successfully with a value of type A. So all of this information you can see just by looking at the type of the functional effect. So just by looking at it, you can know, well, this effect can fail, cannot fail. If it can succeed, what's the success type? Does it have any external dependencies, for example, on a database connection? Or if I'm working with a Spark application, does it have dependencies on Spark sessions? I don't know. All of the dependencies you can see just by looking at the type signature. And well, ZIO is the only data type, the core data type, but the library also provides some useful aliases for simplifying a little bit the code. For example, this type task of A is just an alias for this ZIO data type, where the R type has been set to any. That means it represents an effect that doesn't need any dependency. It can fail with a drawable, or it can succeed with an A. Then we have UIO. This U, by the way, means, I think, unexceptional. So it means this UIO represents a ZIO effect that doesn't require any external dependency to run. It can fail, that's why this error type is set to nothing, or it can succeed with a value type A. Then we have RIO. RIO, because we have an R in the name, means that it's a ZIO effect that requires an environment of type R to run. It can fail with a drawable, or it can succeed with an A. Then we have IO, that has just two parameters, E and A. It represents a ZIO effect that doesn't require any environment. It can fail with an error of type E or succeed with a value of type A. And finally, we have URIO. Because we have this U here, it means it cannot fail. Because we have this R here, it means it requires an environment of type R, and it can succeed with a value of type A. So you can see this is just aliases. I know if you're a newcomer to ZIO, it can seem that there's a lot of type aliases, but when you start writing ZIO applications, you get used to them really quickly, and you don't really need to use them. They are just there as a convenience. And another good thing is across the ZIO ecosystem, where there are other data types besides the core type, the same logic for defining type aliases is followed. So it's really easy to remember with some practice. Okay, so now that we have these basic concepts of ZIO, let's go to the live coding. So I've included the link to the GitHub page here. So you can clone it in your machine now or later if you want. And well, now just let me change my screen. I'm going to share my VS Code so we can start with the live sharing.
Jorge, I think you can give me the link, and I'm going to share with people on the chat.
Yeah, I'm going to paste it in some moments. Okay, so now just let me copy this link for you. I'm going to just a moment, guys. I have this into okay, so I just sent the link to Maya so she can share it with you. Okay, so now let's start with the live coding, the fun part. Okay, so well, as maybe some of you have seen, I've included some starter code in the GitHub repo. So let me explain it first. Here you can see I have this domain package. This domain package has some interesting classes. These are just models of that we are going to need for building the application. I have this model of a board. So as you may know, we have this board in Tic-Tac-Toe. It's a square board. It has 9 fields, right? So I'm representing this board as a map from field to piece. That means I want to track at every moment in which field, in which square of the board, which piece has been placed, if it's empty, or if there is a cross, or if there is a circle that has been drawn there. So that's my model. I have also this model for fields. So this field model, this field abstract class here, represents just all the possible values that a field can have. So, for example, I have this northwest field, north, northeast, west, center, east. So I have just named them according to the position they occupy in the board, in the game board. And as you can see, I'm also associating an integer number to each of these fields from 1 to 9. Then I have this method, this function, that will allow us to construct these field values from strings. Why I need this? Because, for example, if you imagine, we need to ask the user to select in which field they want to put a piece, right? So we are going to ask him, tell me a number from 1 to 9. And according to that, we are going to know which field he has selected. So this input will come as a string. So this is an utility method, an utility function that will allow us to convert it to the corresponding field value. And as you can see here, this make function is a pure function, right? I'm not drawing any exceptions here. I'm returning an optional value of a field. That means just in the case I have these valid inputs that are numbers as strings, I'm going to get a field. And in other cases, I'm going to get a known value. I'm not drawing any exception. So I'm following functional programming principles here. I also have this piece model. This piece model just represents the piece that the player is going to use to play with. So it can be a cross, an X, or it can be a circle, a naught, or an O. So this is just the two possible values for a piece. And also I have similarly a pure function here, this make function, that allows us to get an input from the user as a string and convert it to the corresponding piece. And as you can see, I'm also just returning a pure value here. I'm not throwing exceptions anywhere. Then I have this game result model. This game result just is a model for representing the two possible game results. One result is that someone wins. So in that case, I have a win, and I want to know which is the piece that wins. So did cross win, did circle win? And the other case is that nobody wins, right? There is a draw. So those are the two cases. And here I have an utility function that converts a game result to a string, so I can show it through the console. I have also this player model. So a player can be two possible things, a computer or a human. And finally, I have this state model that models the state of the application at a given time. So the application can be in actually two states. The game can be ongoing. That means nobody has won. There's no draw. So the game must continue. And the other case is when the game is over. So when the game is ongoing, I want to know the current state of the board. So I know which pieces have been put where in the board, who is the cross. So I know here if the computer or the human is the cross, and which turn is it? Is it turn of the cross or is it turn of the circle? And if the game is over, I just want to know the final state of the board so I can show it through the console. So those are the basic models for our application. Well, and also I have here some methods like this. This is computer turn. It's just a helper method that I'm going to use later so I can know if it's the computer turn or not. Okay, so those are the basic models. So let's start implementing our application. As you can see here, I have several methods that I have left unimplemented. Some of them are already implemented, and I'm going to explain what they do in some moments. But now what we need to do is implement the methods that have been left unimplemented. Another important detail is that you can see these imports here. Every ZIO application imports this ZIO library. So this ZIO package contains all the data types that come inside ZIO. I could also do more specific imports, but I'm just importing everything inside ZIO here. You can also see these other two imports. I'm importing here the ZIO console package that gives me access to all the functions for interacting with the console. For example, printing messages to the console or getting information from the console. And I also have this random module. Why? Because I'm going to need to generate some random things in the game. For example, I need to generate at random the computer move, for example. So we are going to use the random module of ZIO. And by the way, inside this import, this is where the ZIO data type comes. Another important detail is that every ZIO application has to extend this app trait. And by the way, this isn't the app trait that comes with Scala. It's actually the ZIO.app trait. So this is a different app from the standard one in the Scala library. So every object that extends this app trait needs to implement this run method. This run method is the entry point for every ZIO application. So you can see it receives a list of arguments from the console as strings, and it must return a ZIO effect. So this URIO, it's just a ZIO effect that requires a ZIO as environment. It can fail and returns an exit code. So that's the contract we must obey. Well, if you are wondering what is this ZIO, this ZIO is just a collection of all the standard modules that come in ZIO. This is just a type alias. I can show it here. You can see it contains clock, console, system, random, blocking. So these are all the standard modules that come in ZIO that give us additional functionality. For example, for this application, we are just using the console module, and we are just using the random module. But you can see here that there are other modules that are provided by ZIO. So this means any application you write in ZIO can use these modules. You have to return a functional effect that doesn't fail. So that means if your application has errors, you need to handle them accordingly. So you have a final functional effect that doesn't fail. If you are not understanding that, there is no problem. We're going to see how that works while we're implementing the application. And finally, this ZIO effect must return an exit code. The exit code is just the typical number you have to return to the operating system when an application ends, right? So if the application ends successfully, a 0 is returned to the operating system, and in other cases, other numbers are returned. So we have to obey that contract. And I'm going to change this to URIO again. It's the same, but it's just shorter. Okay, so let's start implementing our functionality. First, we need to implement this choose player piece logic. So what we need to do here, we need to ask the user, what piece do you want to be? Do you want to be a cross, or do you want to be a circle? So what can we do? We can use this putEster function that comes from the ZIO console module, and this receives what's the string I want to print to the console. So do you want to be cross or circle? And by the way, there is another version, putEster line. The difference with that is that putEster line will add a new line at the end of this string, but putEster doesn't add a new line. In this case, I don't want a new line, So that's why I'm using just this version. By the way, remember this put Esther will return a ZIO effect, a functional effect. In this case, a functional effect that requires the console module from ZIO and succeeds with a unit value, and it can fail. This actually doesn't print anything to the console. It's just a description of printing that message to the console. Okay, so now that we have used this put Esther for defining the message we want to print, next we need to ask the user for the input. For that, we can use getEstherLine. GetEstherLine is a ZIO effect that describes getting input from the console. Okay, so now if I try to compile this, I'm going to get a compilation error. Why? Because it says I require a ZIO effect that requires the console service, that can't fail, that's why this nothing type comes here, and that can succeed with a piece. But I found a ZIO effect that requires console that can fail with an IO exception, and that returns at a string. So I'm not being compliant with this type signature. So the good thing is the compiler can help me, and it will force me to handle the error, the possible errors in this case, because I'm saying this effect should not fail. So I have to do something about that. Where is it failing? It's failing precisely in this getEstherLine. GetEstherLine is a ZIO effect that can fail with an IO exception. So that will be a weird exception that for some reason reading the input from the console failed, right? So I need to handle that exception in some way. So there are several ways we can handle. For example, I could, I don't know, retry reading the input, or I can just ignore that failure. So that's a way of handling an error. In this case, I think I'm just going to ignore the error, because if reading input from the keyboard fails, there is nothing too much I can do about that, right? In that case, my application should just end with an exception, right? So for that, this getEstherLine, which is a ZIO effect, has an OR-die method. This OR-die generates a new ZIO effect that cannot fail. So it's just saying ignore any possible errors that there are, and let's forget this getEstherLine could get any error. So that's exactly what I want to do here. But I'm still getting a compilation error. Why? Because this getEstherLine returns a string, the string that has been read from the user, but I want to return a piece. So now, just for testing, I'm going to change this to be a string. And now compilation is not failing. I'm going to call this method from run. Okay. And well, I'm getting a new compilation error because it says, well, choose_player_piece is an effect that returns a string, but I need an effect that returns an exit code. So for that, ZIO has this helpful operator, exit code, that transforms the output to an exit code. So if the ZIO effect succeeds, it returns a 0. If it fails, it returns a 1. So now the compilation doesn't fail. And now I can run the application. And when I run the application, this run method will be called and will be translated to actual side effects. So this run will be the end of the word, if you want, for this functional application. So let's just run this, what I've done so far, just for testing with SBT run. And let's see what happens. So in theory, we should see this message or circle, and then wait for the user input. Okay, so I see running, the application is running, but I don't see the message printed anywhere. So why is that happening? And well, now it's just waiting for input, and the application succeeded. So why didn't this message get printed to the console? Well, because you have to remember, this put Esther and this get Esther are two separate functional effects, right? These functional effects are just values. So when you write this here, this message is not getting printed immediately, right? This will be printed just here when it's called from run, and these descriptions of side effects are turned into actual side effects, right? So what is happening here is that this line with put Esther is getting discarded. So it's like if it wasn't there. So that's the problem that's happening. Or you can imagine, for example, if you had a method like this one, what will happen with the for? The for will just get discarded. It's a value, but I'm not using it in any way. So something similar is happening when I do this. So I need to combine these two functional effects in some way into just one functional effect, right? Because right now they are completely separate. For that, I can use the flat map operator in this ZIO effect. Flat map is an operator that allows us to chain two functional effects. So first, this effect is executed, put Esther, and once it's succeeded, I can say, what's the next effect I want to execute? So in this case, the next effect I want to execute is get Esther line or die. So now I'm chaining these two functional effects into one. And well, you can see here, I'm just ignoring this. This represents the output from this first effect. And you can see here, I'm just ignoring it. Why? Because it's a unit value. I don't really care about the unit value. That doesn't give me any interesting information. But now this represents just a single effect that first will print this message to the console, and then we'll get this message from the user. So now I can run the application again and see what happens. It should work now, as expected. So it's compiling. Well, I think I've compiled the previous version. Okay, so no problem. I just run this again later. Okay, so it should have shown this message when running, but it seems I needed to clean the previous compilation. But no problem. Let's just continue so we don't end with time. Okay, so I've said that this is a way of chaining two ZIO effects. So we're going to use that. And well, this was just for testing. So I will change this to be as it was before. I'll leave this unimplemented. And I will continue with this. Okay, so now if I try to compile this, I'm going to get an error. Why? Because this returns a string, and I again want to return a piece, right? So I need to add some more logic to returning a piece. Before doing that, instead of using flat map, because we are in the Scala programming language, we can use a better feature of Scala, that's for comprehensions. So for comprehensions allows us to write applications without having to call flat map or map. Map is also another method that comes in ZIO functional effects. So this will allow us to chain also ZIO effects in sequence, but using a nicer syntax that's more similar to how we program in imperative programming, right? So what I'm going to do here is I'm saying first I want to print a message to the console. Next, I want to get the input from the user. This means exactly the same as before, but now you can see we have a nicer syntax, where in each line we have the action we want to execute. And the Scala compiler under the hood will transform these calls inside the for comprehension to be calls to flat map. Okay, so now I have the input that has been introduced by the user as a string. Now I want to convert that input to a valid piece, right? So for that, in the piece object, I had this make method that receives a string and returns a piece. But it returns a piece inside an option, right? Because this input can be invalid. The valid inputs are X or O. If I introduce another input, I'm going to get a non-value. So that's good, but now we have a new problem. And the problem is that in a for comprehension, we need to use the same data type in all the lines of the comprehension. So this put Esther returns a zero effect. This get Esther line returns a zero effect, but this make method returns an option value. So it won't work. So I need to convert this option to be a ZIO value. For that, ZIO has a constructor, ZIO from option, that allows us to convert an optional value, an option, to a ZIO effect. This ZIO effect will succeed if this option represents a concrete value, and it will fail if the option represents a non-value. Okay, so we have this converted now to a ZIO effect, but I'm still getting compilation errors. Why? Because this effect says that it can fail. Remember, this URIO means it's an effect that cannot fail. But here I'm saying there are cases where failure can occur, can happen, right? In the cases where a user introduced an invalid input. So what we do if the user introduced an invalid input? Well, we can ask the user again for a new input. So ZIO has an interesting operator we can use here called or else. So this or else operator, this is an operator on ZIO, allow us to execute a fallback effect in case the first one fails. So if this first one fails, it means the user introduced an invalid input. I need to ask the user for a new input again. So I can print a message with put extra line, invalid input. And once I've printed that message, I want to choose a player piece again. For that, I can chain with flat map, as we have done before. I'm just discarding the output of put extra line because it's just a unit. And I can call choose player piece. Okay, so now I'm not getting compilation errors, and I can just return this piece. So here you can see I'm calling this choose player piece effect in a recursive fashion. So that's another characteristic of functional programming, right? We don't use loops for doing iterations. We use recursion. So, well, this compiles now. So it means it does what exactly what the signature says. It says it depends on console. It can't fail, and it returns a valid piece. There are some things that can be improved here. So let's, I'm going to make some changes. For example, I can combine these two here. There is another way of combining ZIO effects besides using flat map, besides using for comprehensions, and it's the zip method. Zip allows us to combine two ZIO effects into one effect that succeeds with a tuple. So I can call zip here, and this will return a containing the result of put Esther and containing the result of get Esther line. Here. So you can think this is as a ZIO effect that can succeed with a unit value, a tuple of a unit, and a string. This is the success type we're going to get when calling this zip. But I don't actually need this unit, right? Because it doesn't say any interesting. I just want to know the input from the user. So there is a variation of this zip method called zip write. And zip write just returns the right value of this tuple. So it will return just a ZIO effect that succeeds with the string. So that's better. And there is a nice symbolic operator for this. Instead of writing zip write, I can write this symbol. This is equivalent to zip write. And now I have a ZIO effect combined in just one line that prints this message and gets the input from the user. And this combined effect will return the input. So I've reduced one line of code, if you want. Another improvement I can make here, instead of writing or else, I can use this symbolic operator that means or else. And instead of using flat map here, I can use again this zip write logic, right? So I can, instead of using flat map, I can use zip write. So the basic difference between flat map and zip is that in zip, the second effect doesn't depend on the result of the first effect, right? And in flat map, you really need the output of the first effect for doing something with that output in the second effect. In this case, that wasn't needed, and that's why I can use zip write. Okay, so I have this method implemented. And another change I can make here is, instead of using def here, I can use a val. And why is that? That's because, well, if I maintain this as a def, it will work. But a def is evaluated every time you call it, right? That's how Scala works. So it means every time I call choose player piece, this for comprehension will be evaluated. But we know this returns a ZIO effect. A ZIO effect is an immutable value. So it means that no matter how many times I call this choose player piece, I'm always going to get the same result, right? So if I'm going to get the same result, I just need a val. Making it a val will make that this for comprehension is just evaluated once, the result is stored, and it can be reused many times, all the times you want. Okay, so next part of the application, let's implement this method, which piece goes first. So this should choose at random what's the piece that goes first, cross or circle. For that, I can use this next Boolean function that comes from the ZIO random module, and this will generate a random Boolean, so a random true and false, right? But I don't want to return a Boolean, I want to return a piece. So I need to transform this randomly generated Boolean to a piece. For transforming a ZIO effect, you can use this map method, this map operator. Map will receive a Boolean. In case it's true, I can return, for example, a cross. And in case it's false, I can return a circle. So now compilation is going okay. I'm returning a piece. This effect isn't failing, so it's already done. And I'm changing it to a val as well. The program loop, well, I'm going to implement this later. Then I have this drawboard method that I have already implemented. I'm not going to go into the details of what this does, but basically this is just for drawing the board, right? So this builds a string that contains the drawing of the board, and I'm printing it to the console using put line. So this returns an effect that describes printing the board to the console. And later, you can analyze it with in more detail if you wish. Next, we have this step function. This step function is very important for the logic of our application because it will allow us to move the game state step by step. So we have an input state and we have an output state. So what does this step method do? It checks the current state of the game and sees if it's computer turn. If it's the computer turn, I need to get the computer move, right? And in other case, I need to get the player move. So I need to ask the player which in which field, in which part of the board we want to place your piece, right? And after having obtained the next move from the player, I can take the corresponding field in the board. And as you can see, this get computer move, get player move, and take field, all of them are functional effects. So I'm combining them using for comprehension here, as I've done above. And this will return a new ZIO effect with the next state of the game. And you can see here also, this is interesting, you can see in the type signature here that this is a ZIO effect that cannot fail and that requires the random module and the console module. So this is a very good example that shows how ZIO helps you with seeing at any moment what are the exact dependencies of your application. You can see here precisely that you depend on two modules, and you can depend on very modules, not just two. So that's really powerful. Another thing I want to mention here before I forget, you don't really need to write this type here. You can just write this method like this, and it will work. Scala is automatically able to infer the type of this ZIO effect without you needing to write it. So if I position the cursor over a step here, you can see this is a ZIO effect that depends on random and console, it can't fail, and returns a new state. That's the correct type. So ZIO is designed in a way that's completely type inferable. Scala can infer automatically the types for you, but I'm going to keep it here because having the advantage of having the types written here specifically is that serves like a kind of documentation. Okay, so now let's implement get computer move. So for getting the computer move, we actually need to generate a move at random, right? So that's why this effect requires the random module. So basically, the computer has to choose at random one number from 1 to 9. That number means which piece of the board should be used. So for that, I can generate this integer using nextInt bounded. This is a function that comes inside the ZIO random module. And this expects to receive the maximum random number you want to generate. For that, I'm going to pass this value. So I have this unoccupied fields list of the board, and I want to know the size. So here I'm generating just a random number. For example, if I have 4 unoccupied fields in the board, this will generate a random number between 0 and 3. So it's just obtaining an index of unoccupied fields. Next, once I have that random index, I'm going to obtain the corresponding field in the unoccupied fields list. So after this, I already have a random field. And that's all that I need. I don't need to do anything else. You can see the code is already compiling. But I want to add some more things. For example, I'd like to tell the user, well, the computer is, we are waiting for computer's move. So press enter to continue or something like that. So for that, I'm going to use another method here in ZIO called tap. Tap is a method that receives the success value of this ZIO effect. In this case, the success value is a field. And it does something with it on the side and returns the same success value of this effect. So this is useful for doing some things on the side, but we still want to return the original success value. So here, I don't really care about what field has been generated. I just want to print a message using puts_line, waiting for computer's move. Please press enter. Right? And after that, I want to get that enter from the user. For that, I need to use get_line. And I'm going to call or die on that effect because I don't care if that get-str line fails. But this get-str line is an effect, and all this thing here is another effect. I need to combine both of them. I can use zip, for example, or I can use zip left. This is another version of zip. So in the case of zip left, this left effect and this right effect are combined into just one effect, but just the return value from the first one is returned. So in this case, I just want to return the field, the random field that has been generated here. I don't care about what has been entered here because I just was waiting for the enter value, right? And I don't really care about it. So now with that, we have the logic complete here. Now let's implement a get player move. So for that, I'm going to start a new for comprehension. Why? Because I'm going to need to change several ZIO effects. Okay. First, I need to ask the user for the input, right? So I can print a message with put Esther, and I can tell the user, what's your next move? And it must be a number between 1 and 9. And after that, we can call get_line for die, right? So after this, input will be a string containing the user input. Next, we need to convert this input to a field, right? So for that, we have this field.make method that receives an input string and converts it to an option of a field, right? So if the input is the expected value, a number from 1 to 9, this will return a field. And if not, it will return a known value. This is an option, right? So again, I need to convert this to a ZIO effect using ZIO from option, right? And after that, I have an effect that can fail in the case that the input was invalid. What I need to do here, I need to write a fallback effect that in the case the input was valid, we need to ask the player move again. So I can use or else, and I can write a message to the console and say invalid input. And after printing that message, I can call get player move again with the same input word. So now everything is compiling. We have an effect that can't fail anymore. But there is one more detail that we need to take care about here. And is that the player, for some reason, could have chosen a field that has been already used before. So we have to check that if the field that the user has chosen hasn't been used. So for that, I'm going to say if. And inside the port, I have this utility method field is not free. And I pass the field that the user has chosen. So if the field is not free, so if it has been already used, I can print an error message. I can say that field has already been used, right? And after that, I can get the player move again. And in the case that the field was not occupied, it's free, I can just return the original field that has been selected by the user, this temp field. So I can return that. But now I'm getting a compilation error. Why? Because you can see this temp field value is just a field, right? And we need to return a ZIO effect because this for comprehension is all working with ZIO effects. So I need to convert this to a ZIO effect. So for that, there is another constructor called ZIO.succeed. ZIO.succeed creates an effect that succeeds with the given value, in this case, temp field. And now compilation is working, and I can just return this field. So great, so now we have this method for getting the player move. Now we need to implement this method for taking a field in the board. So we know what field has been selected by the computer or by the player, and we need to put that piece, the corresponding piece in the board, right? So we need to update the state. Okay, so I'm going to start another for comprehension here. And we need to return an updated state, right? So first, I'm going to get an updated board. This updated board will be the original board we have. That board is inside this state. And we need to update it with the new move that has been made by the player. So I can call state.board.updated. This is an utility method I have in board. I can pass the field that has been chosen by the player and the piece. It's a cross or circle, right? We can obtain that from state.turn. But I'm getting a compilation error because this is a board value. It's not a ZIO effect. I want to return a ZIO effect. So again, I can use ZIO.succeed to get a ZIO effect there. Once I've updated the board, I can update the term. So what's the next term? Is it a cross or circle? So I have the current term, state.term, and if I call this utility method next on it, I'm going to get the next term. Again, this returns just a piece. I can convert it to a ZIO effect using ZIO.succeed. Okay, so next I need to get the game result. So maybe someone already has won, or there is a draw, or maybe the game must go on. So I'm going to obtain the game result by calling this getGameResult method. And I need to pass the updated board to that method. This method, getGameResult, is already implemented here. And you can see it returns a ZIO effect that cannot fail. And it doesn't have any requirements. That's why this is a UIO. So it doesn't depend on the console. It doesn't depend on random. And it returns an option of game result. So first, here I'm checking who is winner, if cross or not, or circle. So I check if both of them won. That's an illegal state, right? It never should happen that both players win. So in that case, I'm returning a ZIO effect that immediately dies with this illegal state exception. In other cases, if cross wins, I return a ZIO effect that succeeds with game result that win, and piece X. Something similar when knocked or circle wins. In the case the board is full, it means there's a draw. That's what I'm returning here. And in other case, it means nobody won, there's no draw. So there's no game result yet. The game is still going. So in that case, I'm returning a known value, but encapsulated inside a ZIO effect. So I could have done something like this, succeed with known, but ZIO has a shortcut, and instead of using that, I could just use UIO.known. And this returns an effect that succeeds with a known value. And by the way, here, I'm using this as sum method that converts this ZIO effect. This ZIO effect succeeds with a game result, but as sum transforms it to succeed with an option of game result. This is similar. I could have done this instead. And it will work, but I have this interesting shortcut from ZIO, so I'm just using it. Okay, so this returns the game result inside a ZIO effect. I'm obtaining it here, and now I need to analyze it for obtaining the next state of the game. So I use, and this is an option, so I can do a pattern match here, another interesting characteristic feature of functional programming. And in the case I do have a game result, it means I already know who won the game. I can just print it to the console For that, I have this utility method show in the game result object. And after that, I can succeed. I need to return, as it says here, the new state, right? And the new state in this case will be that the game is over. And I return the updated board. In the other case, if there is no game result, it means the game is still going, right? So I need to succeed with state of ongoing. And I need to pass the updated board and I need to return the updated turn. So I think everything is good. Let me. Oh, sorry. I'm just going to copy the original state and update the board and the turn, right? So now I have the new state, the next state, and I'm just going to return it. So I have this take field method already implemented. So get game result is implemented. Well, this is winner is used inside this as utility method. You can analyze it later. But I think we have pretty almost everything. We just need to implement this program loop. This program loop will call the step function, so the game can proceed. So we start with an initial state, and we're going to analyze that state. So in case the game is ongoing, we have a board, we have quiz cross, and a turn. I don't really need this, I think. I need first to draw the board. I'm going to draw this board inside the state here. And after I've drawn the board, I can proceed with the next step. So I can call the step function that takes an state. This step will return a new state, right? So after having the new state, I need to call program loop again in a recursive fashion. For that, I can use flat map that receives the input from this step, the output from this step function, that will be the next state. And I can call program loop with the next state. So this will be recursive, right? And I can just simplify it like this. And it works. And in the other case, when the game is over, well, in that case, I just need to draw the board. And that's it. I don't need to call the step function because the game is already over. Okay, so this will be the loop of our application. Now we have everything, and we need to call it inside run, the run method. That's the entry point for every ZIO application. So we are almost there. So we have this for comprehension here. Okay, first, what I need to do in the game. I need to obtain the player piece at random. For that, I have this choose player piece method, ZIO effect. Next, we need to determine what's the piece that goes first. Piece that goes first. I have this ZIO effect, which player goes first. And just for fun, I can use tap for printing a message to the console saying what's the piece that's going to go first. Right? So, okay, I have the piece that goes first. Then I can create an initial state, the initial state of the game. So this has to be an ongoing state. And first, we're going to start with an empty board. We are going to say what's the player that will go. What's the player that will be the cross? So I need to say if player piece equals cross, it means the player, the human player, is the cross. In other case, the computer player is the cross, right? And finally, we need to say what's the piece that goes first. So I can just use this value. So I have an initial state, and once I have an initial state, I can call the program loop, the main logic of the application, with the initial state I've just built. This program loop returns a unit value. So I don't care the return of it. That's why I'm using underscore here. I can yield unit here as well. Now I'm getting a compilation error. Why? Because I'm returning an effect that succeeds with a unit, but I need an effect that succeeds with exit code. So I can just call exit code in this whole ZIO effect. And now the application is compiling. Okay, so I think we have everything we need. So let's try running the application. And let's see if it works as expected. Maybe I've missed something, but we'll see. I think everything is as it should. Let's just, okay. Okay, so the message, do you want to be cross or circle? I want to be cross. And it says circle goes first, waiting for computer's move, press enter. It seems the computer has chosen 5. I will choose 1, waiting for computer's move. Computer has chosen 3. Let's say I choose 7. And now waiting for computer's move. Computer has chosen 2, and I can choose 4. And cross wins, and the application ends. So it seems everything is working as expected. And well, I'm going to push this solution to GitHub as well, so you can take a look to it more carefully, look at the details and play with it. So yeah, that's it for the live coding session. Let me share my last slides before we proceed to the questions. Okay. So where to learn more, I have introduced some links here at the end of the presentation. There are some interesting articles in our Scala blog. For example, this introduction to programming with ZIO functional effects. It's a similar thing to what I've done here, but this implements a hangman game instead of a tic-tac-toe. So if you haven't seen it, you can take a look to it. There's also a Spanish version of that article. So for those of you who speak Spanish, you can also take a look to the Spanish version. We have this mastering modularity in ZIO with Z-layer ebook in the Scala blog. So this is like the next step of building this tic-tac-toe game. So in this ebook, you'll see how you can build the application in a more modular way. Because as you have realized here, I've put all the logic, practically all the logic inside the tic-tac-toe object. But in this ebook, you can see how Z-layer, who is that is another data type in the ZIO library, can help you to build the same application, but in a more modular fashion. There's here another interesting article on how to write concurrent LRU cache with ZIO STM. So you can see the power of using ZIO for building concurrent applications. So this is a really interesting one for those of you who are interested in the concurrency part. You have also the ZIO official site and Zionomicon. Zionomicon is the official ZIO book. So you can take a look to it and you're going to find a lot of great information inside there. It's written by the authors of ZIO. So that's a pretty great source of information. And well, you can also learn how to use the full potential of functional programming with Scala trainings. So if you're interested, Scala offers trainings, for example, Scala 2 for Java developers, if you are completely new to Scala, or Scala 3 for Scala 2 developers, where you're going to learn all the new and great features of Scala 3. And we also have trainings for ZIO. We're hiring, so Scala is looking for Scala developers. So if you're interested, you can take a look to the careers page of our Scala.io site, and you can contact Maya on Twitter or by email. And I don't know why the icons here got inverted. It's interesting, but okay. So here you have the Twitter handle and the email, so you can ask Maya if you have any more questions about recruitment in Scala. And finally, you can contact me if you want to ask any questions. Like, here's my Twitter handle, my LinkedIn, and also by my email. So thank you.
Thank you, Jorge, for your presentation. You have one question. I sent it to you, so you can answer it now.
Okay. Okay, what happens to a stack during execution of program loop, or in bad input during execution of choose player piece? Okay, so let me just share again my screen with the code so we can see it. Here it is. Okay, so choose player piece. Okay, so in this case, well, I suppose you're asking about this part here. What happens in case this get_str line fails, right? Because I've said this method can fail with an IO exception. And well, ZIO makes an interesting distinction between failures and defects in your application. So failures are things that you can handle as a developer, and you should handle them. But there are things that there isn't a real good way to handle them. For example, if introducing input from the keyboard fails for some weird reason, it almost never happens. At least it never happened to me. But if that failed, well, what can you do in that case? I think there's not so much you can do. So in that case, that's why I'm using this or die method. And for ZIO, this means that it's like we are forgetting this get_str line can fail. But if it fails, the application will just die with an exception. But this is different than drawing an exception. So this is still a pure functional effect. This is an effect that describes drawing an exception in that case of failure. But no exception is actually drawn here. The exception will be drawn just in case this get_str line fails, and that will be when the functional effects are actually turned to side effects when this run effect runs. And you have also asked about the stack, right? And you could think, for example, here in program loop, or yeah, just by looking at this function, you could think this can give stack overflow errors, right? Because this function is not tail recursive. Because here program loop is not the last call that you are making in this recursive function, right? Actually, the last call is a flat map. But you can say this function is effectfully recursive. So the interesting part here is ZIO has internally an implementation that takes care of this for you. So you don't have to care about if you're writing a tail recursive implementation or not. The ZIO internal implementation will handle this, so you will never have stack overflow errors. Okay, what other questions? Well, is the choose player piece tail recursive? Well, this is not tail recursive as well, but is effectfully tail recursive, right? Because here, again, choose player piece is not the last thing that is called in this function, right? In this ZIO effect, the last thing that's called is zip right? But because ZIO does, because of the internal implementation of ZIO, this will be effectfully tail recursive. So you don't have to worry about having stack overflow errors. Excellent, thank you. Please push solution in a different branch. Sure, I will push the solution in a different branch to master, so every one of you guys can take a look to it later and play with it. So I think we don't have any more questions, Maya.
No, I don't see anything more. Thank you very much, Jorge, for your presentation. I can see people very like it. I would like to say that this presentation is recorded, and we're going to share it on our social media, and also it's going to be available to watch later on YouTube. Again, so don't worry if you were late. You can watch it again. Again, thank you, Jorge, for your presentation. It was amazing, and yeah, see you next time.
Yeah, see you next time, and thank you everyone for attending, and I hope you enjoyed it. So thank you. See you.
Thanks.
Bye-bye.